You know, our planet's environment is this huge, super complex chemical system. The best way to think about it is like a giant balance sheet. You've got all these natural inputs and outputs that, ideally, keep everything perfectly in check. But what happens when we start adding things that just don't belong? Well, that whole balance gets thrown way off. So let's dive into the chemistry of our air and water and see what's really going on.
Just take a look at this. This is photochemical smog hanging over Beijing. It's such a powerful picture of what happens when that planetary balance sheet goes deep into the red. And that's not just fog or haze you're seeing. Nope, it's a complicated chemical soup, and figuring out what's in it is absolutely crucial for our health and for the planet's.
All right, so here's our game plan. First, we're going to establish the baseline, what's actually supposed to be in the air. Then, we'll get into the chemistry of pollution itself. After that, we'll look at the consequences, this crazy chain reaction that happens. But don't worry, it's not all doom and gloom. We'll explore some really cool solutions, and finally, we'll shift our focus from the air to our water.
Okay, first things first. Before you can really understand pollution, you've got to know what it is you're polluting, right? So let's set that baseline and take a look at what clean, fresh air is actually made of. So the recipe for clean air is actually pretty simple. It's almost entirely made of just two gases. As you can see, a whopping 78% is nitrogen, and another 21% is the oxygen we breathe. That's 99% of the air right there. Everything else, like argon and a little bit of carbon dioxide, is crammed into that tiny 1% left over. Pretty wild, huh? And when you remember that smoggy picture from a second ago, you really get a sense of how much we've messed with this natural recipe. Okay, so if the air all around us is this mixture, how do we pull the different parts out? I mean, how do we get pure oxygen for hospitals or pure nitrogen for making fertilizers? Well, the answer is a really cool process that takes advantage of one key difference between all these gases.
And this is the machine that does it. It's called a fractional distillation column, but you can just think of it as a sorting factory for gases. It all works on one simple principle. Every single gas in the air has its own unique boiling point. That's the exact temperature where it turns from a liquid back into a gas. This whole machine is designed to use that one simple fact to sort them out perfectly.
So here's the play-by-play. First, you take regular air and you cool it way, way down to about minus 200 degrees Celsius. So cold, it actually turns into a liquid. But before you do that, you got to filter out the water and carbon dioxide because they just freeze solid and clog up the whole system. Then you just gently, gently warm that liquid air back up. The gas with the lowest boiling point turns back into a gas first. And who's that? It's nitrogen at a super chilly minus 196 degrees Celsius. It bubbles off and gets collected at the very top. Then comes argon and then oxygen, each one collected at a different level. It's so clever.
Okay, so we've got our baseline for clean air. We know what it's supposed to look like. Now it's time to introduce the disruptors, the pollutants. These are the unwanted chemicals that show up as massive debits on our planetary balance sheet, throwing the whole thing into chaos. Let's meet the usual suspects. First up, carbon monoxide, or CO. This stuff is made when fuel, like in a car, burns without enough oxygen. It's basically a silent poison. It's so dangerous because it actually sticks to your red blood cells way better than oxygen does, so it starves your body of oxygen. Then you've got sulfur dioxide, mostly from burning fossil fuels like coal and power plants. And finally, nitrogen oxides, which are created in the crazy high temperatures inside a car engine. And you see the pattern here? Both sulfur dioxide and the nitrogen oxides are the main ingredients for acid rain. Now here's the thing. These pollutants don't just stay put. They get up into the atmosphere and they kick off these massive chemical chain reactions. The result? Huge planet-wide consequences. We're not just talking about one smokestack or one tailpipe anymore. We're talking about the global fallout. And here's exactly how one of those big consequences happens. Acid rain. So when sulfur dioxide and nitrogen oxides get pumped into the air, they drift up into the clouds. Up there, they mix and react with the water droplets, and this chemical reaction creates sulfuric acid and nitric acid. Basically, the clouds become acidic, and what goes up must come down as acid rain. And the damage this stuff causes is just devastating. It can kill entire forests by stripping the soil of essential nutrients. It literally eats away at buildings and statues, especially ones made of limestone, and it can make lakes and rivers so acidic that fish and other animals just can't live there anymore. It's a chemical problem that starts in the sky but causes total ecological disaster on the ground. Not for another major consequence. the greenhouse effect. Now, the greenhouse effect itself isn't a bad thing. In fact, it's essential for life. You can think of it like Earth's natural, cozy blanket. Certain gases in our atmosphere trap just enough heat from the sun to keep the planet warm and comfy. Without it, Earth would be a frozen rock. The problem starts when we pump more of these greenhouse gases into the air, especially carbon dioxide and methane from burning fossil fuels. It's like we're taking that cozy blanket and making it thicker and thicker and thicker. More heat gets trapped, less of it can escape back into space, and the whole planet starts to warm up. And that, in a nutshell, is the driver behind global warming. Okay, I know that all sounds pretty bleak, but this is where the story starts to turn around. Because just like chemistry helps us understand the problem, it also gives us some incredibly powerful solutions. Let's look at how we can actually use chemistry to clean up this mess.
Let's start with a brilliant piece of technology that's in almost every car on the road today: the catalytic converter. It's a little box in the exhaust system, and inside it's got this honeycomb structure that's coated with really precious metals, like platinum. And these metals act as catalysts, which means they can make certain chemical reactions happen incredibly fast. And here is the beautiful, brilliant chemistry that's happening inside that box. Look at this. Remember those nasty pollutants from earlier? You've got poisonous carbon monoxide, CO, and then nitrogen oxides, NO, that cause all that smog. This one reaction takes those two toxic gases and, in an instant, converts them into harmless carbon dioxide and nitrogen, which, remember, already make up 99% of our air anyway. It is a perfect example of using chemistry to solve a chemical problem. Now, on a much bigger scale, nature has its own amazing system for dealing with carbon dioxide. It's called the carbon cycle. It's this incredible global network where some processes, like us breathing out, release CO2 and other processes absorb it. For millions of years, this cycle has kept everything in a beautiful, stable balance. And the undisputed champion on the removal side of the carbon cycle is photosynthesis. Seriously, just take a second to look at this equation. It's the engine of life on Earth. On the left, you got our big problem, carbon dioxide, plus water. Then, using a little bit of sunlight, plants turn that into glucose, which is sugar, the food that powers nearly every living thing. And, as a byproduct, they release the very oxygen that we need to breathe. It's the most important chemical reaction on the planet.